So next, how are we going to apply this to speech? Okay. So again, I have to remind you, I have actually gone away from speech for a few days. So let me remind you, if I am talking about speech recognition, what is the problem? I am trying to take a speech signal, right, and then convert it to a sequence of sounds or phonemes. Then I will use a lexicon to convert the sequence of sounds to every word has a unique pattern of sounds, and so I find the sequence of words or the words from the lexicon and then form a sequence of words for a sentence. Okay. And so one of the important aspects of this is the Gaussian mixture model, the hidden Markov model problem, right. So just to remind you, this is analogous to our weather prediction problem. So if you recall, so let me remind you what we did in GMM HMM. So recall, first what we are doing is weather prediction, right. So let me look at weather prediction, right. So what we are saying is the states, the sunny, cloudy and rainy is something that I cannot observe. So cannot observe, I am deep inside a cave, so I cannot observe, and therefore it becomes hidden, I cannot observe it. Okay. But I observe a related phenomenon, which is grass, condition of grass, which is wet, damp, dryish and dry or something, right. So there are 4 conditions. Okay. And this, given one day sunny, what is the probability of next day being cloudy? That is referred to as transition probability, right. So this is called transition probability, and this one, probability of what, of it being grass being, having observed, 2 ways you can do, it's basically likelihood versus posterior. So probability of sun given grass is dry, right, is basically going to be what we call as observation probability. In fact, we do the other way around. So probability, so we do the other way around, grass dry given outside is sunny, this is called the observation probability, right. So I see the outside weather, and given the outside weather, I see how often does it grass be dry or this, because that is what I can observe, right. I can observe this. Okay. So so this is usually represented as Aij going from the ith state, example sunny, to jth state, example cloudy, correct. That is what we do, and this is probability that grass is dry given. So we form like this, no. So given that the grass condition, right, given it is sunny, for it to be dry, dryish, damp and wet or soggy, right. So we have some probability, some 0.6, 0.2, 0.1 and 0.1 or something, right. So this measurement is there. So given it sunny, how often this is there? This is called observation probability. So it is like usually given by the notation B, given sunny, what is the probability of dry? Okay. So this is equal to probability of grass dry given outside weather sunny. So in this hidden Markov model, we cannot directly observe something, that is in this case the weather condition sunny, cloudy, rainy, and but you can observe a related event which is the condition of the grass, and therefore we need these two probabilities, and so this is a hidden Markov model. So how is this applied to speech? So for speech, what we have is a waveform, correct? And we have done this multiple times. We are going to take some kind of a windowed representation. So we look at a small window of 25 milliseconds, right? 25 milliseconds. This is 25 milliseconds, right? 25 milliseconds. This is 25 milliseconds, and each one of them, this interval is 10 milliseconds. Okay, so this is in practice, this is 10 milliseconds. Okay, so this is something by default, after doing many experiments over years, people have figured out this is best combination of numbers. Okay, so for each one of them, for the green one, I will extract some MEL filter bank features or MFCC features. We have already discussed it some 10 classes back. So please look at it. So this is the MEL filter bank features, or MFCC features, something that's useful in the speech domain, right. So for example, if I am trying to classify between men and women, I use heights and weights as two features, right, and that helps me separate the class of men from the class of women. For this, for what we are interested here is sounds, and for sounds, the vocal tract changes, and mouth and tongue and all change. So the frequencies change. So we have to look at the frequency content, and that is being captured by the MEL filter bank features. Similarly, for this guy, I will get another vector O2, and the third vector will, so on. Okay, O3. And all of these are there. Okay, usually this will be some 80 cross 1 vector or something, right. So this will be some 80 cross 1 vector. Okay, so they are all same vectors, 80 cross 1, it's 80 cross 1, something like that. Okay, so these are important information that we are trying to extract from the speech signal, the features, right. So now what is our objective in speech? We want to know what sound or phoneme. Okay, so when I speak, I am producing different sounds like ha, a, n, d, an, d, I, g, o, g, like that. Different sounds are produced. But when I speak fluently, it transits, right. So they are different sounds. So the sound is varying, right, it is changing, the phonemes are changing. So what I am interested in is finding out. So if I look at this particular, let us say look at this particular guy, right. So this is a particular guy, I have, right. So let us say I am looking at this particular guy. Okay, this is what I observe. From this observation, I extract O1, right. I am interested in knowing what is the sound here, right, but I cannot see the sound, right. I cannot right now, I only the waveform, right. So that is hidden from me. So what sound or phoneme is hidden from me? It's hidden from me, right. It's hidden from me. Okay, but this is analogous to sunny, cloudy, etc. hidden, right. Let us say I am this saint who's deep inside a cave. I cannot see the outside weather condition. So that is not available to me. I don't know what it is, but I observe a related phenomenon. Okay, so I can measure this. or observe, right? This is a related phenomenon, right? This is a related phenomenon, right? So, since I can observe it, this is analogous to observing the condition of the grass. Okay. So, given O1, do I know is it, so given O1, given I observe O1 is the sound or phoneme, whether it is A or E or E, right? E and E, U or K or P, whatever it is, right? So, so if you are looking at Devanagari, is it or K, is not the written form, the sound, the spoken form. Okay. So, that is what we are trying to capture. So, speech recognition, we are only worried about this. Similarly, if I go to the next 25 milliseconds, so from here to here, I will get another 25 milliseconds. So, this part of the signal, what does it correspond to? We are changing sounds. You see, first part can be a, second part can be n, third part can be d, and so on. Okay. So, we are capturing that, and so, but we don't know which of the sounds are there, right. So, because we can't see them or we can't hear them. So, that is the basic idea of hidden Markov model, and therefore, we modeled. So, this guy is going to be taken care of by the transition probability. This is more a structure of the language. So, certain sounds can occur one after the other. So, there is a structure, certain sounds occur more often after another sound, certain sounds very rarely occur after certain sounds. These are spoken, not the written part. Okay. This is the equivalent of observation probability, right. So, this is the observation probability. And when I did the conventional GMM-HMM, because it is the same sound, but it is produced by men, women, children with different kinds of vocal tract shapes and lengths and so on, there, even though to a human it sounds like the waveforms and therefore the spectra and therefore the because of environment and because of speakers, variations, environment noise, etc., right, etc. For each sound, example, or something, OI, the MEL filter bank features exhibit a lot of variability. And that is what we have talked about many times. If I look at the heights of people, right, so it is going to be as a Gaussian, right. But if I have multiple speakers, multiple population consisting of men, women and children, then you will get three different kind of peaks, right. So, this will be, so this is men, women and children, they form their own subpopulation Gaussians, right. So, and the best way to model this is use a mixture of Gaussians to model, right. And so, this is modeled by a mixture of Gaussians. Therefore, in speech recognition, we always talk about HMM GMM or GMM HMM models, right. So, that is the the conventional way of doing things. Now we are going to use deep learning based methods, right. So what does deep learning guys tell you? So the deep learning guys tell you that in a conventional method, what do? I take the features, try to get model it as a mixture of Gaussians, right, and then use the phonotactics, the given one sound, what's the probability of another sound and all, with the help of HMMs, and then model the entire thing, right. Now I can project or do the same problem where I can replace the Gaussian mixture model by a deep neural network. So the idea in a deep neural network, it's not replacing the, so that's why it's called a hybrid model, that the GMM part will first be replaced by the DNN, the deep neural network. How am I going to do that? The way I am going to do it is I am going to take these features, right. I am going to do some non-linearity and then I am going to apply a softmax to predict. So let me project the way that I will be putting it. So we now, so GMMs replace with deep neural network. So this is also called hybrid model. Why is it hybrid model? DNN is deep learning kind of thing, but I still will need an HMM. So it is basically statistical still. So it's a hybrid between the statistical and the deep learning approaches. Okay. So what is the GMM doing? So the GMM, the basic idea in a GMM is that you give me a big some 25 millisecond, I get a feature vector O1. Okay. So I want to know what sound, what phoneme, right. So it's a classification problem. So I am basically doing a classification problem. So given this particular waveform, right, what class, what sound does it belong to, what sound was produced. So that is my fundamental question. So similar to whatever we did for GMM, if I had height like this, a GMM measuring the height, right. So this is actually coming from children, this is coming from women, and this is coming from men. Now the question is, do I know which class, does it belong to the class of men or women or children? That is what I am trying to find out. Okay. So that I can do it with the for heights. Here I am going to do a very similar idea, that I am going to ask, given given that I am sound is a, or phoneme is a, what is the probability? So I have a GMM for a, which I have trained, which I'll we have explained together. We need many times go back to the GMM HMM slides, and you'll see I can build a net using what's called embedded re-estimation, which is basically some kind of iterative algorithm, right, like expectation maximization. So given the model GMM for R, what is the probability or likelihood of generating O1, right? That's what we are trying to measure. Okay. So instead of that, so we are trying to somewhat predict that given the observation, what class does it belong to, right? So I can post that as a DNN problem. So but it will be a posterior. So given the measurements O1 here, these are the input nodes. So this is my measurement O1. This is the input node. Then there is this hidden layer. So, I have one small 25 millisecond waveform, right. So, this is 25 millisecond waveform. Based on the 25 millisecond waveform, I get the O1 vector, which becomes my input node. Then I have the hidden layer, and my task is to recognize what? Recognize which of the, let us say there are 45 phonemes, right, which of the 45 phonemes it belongs to. So, there is exactly similar to what I told about 0 to 9. So, here instead of 0 to 9, I am trying to find out which is, which phoneme class. So, there are 45 phoneme classes instead of 10 classes. So, it is a 45 class problem. So, obviously, I am going to put a softmax here. So, there will be a softmax here, softmax, okay. So, softmax, okay, and my problem is I have to determine which of these classes it belongs to. So, if it belongs to the, so this could be the R class, this could be the E class, this is the E class, this is the Ker class, this is the J class, something, all 45 phonemes or something. So, it is a pattern classification problem, and I can have deep, means I can have multiple no layers and so on, and try to do this problem, okay, and it works very well. It works much better than the GMM, okay. So, there is a slight difference. This is what we call as a posterior. So, basically this is going to be what we call posterior. This is something to do with statistics, likelihood versus posterior. It's sort of related, you need the prior information and so on. So, do not worry. So, the GMMs are basically likelihood kind of measurements, and DNNs are posterior measurements, but nevertheless they are related, okay, and therefore we can use this in a GMM, DNN-HMM. So, that is what we are going to do, okay. So, in a DNN-HMM we are going to replace the GMM with the HMM, that is the only difference, okay. Now comes another interesting idea which I will mention and motivate you. So, now just for your revising what you are saying. So, suppose we have an HMM for utterance yes, right. So, there are three sounds yeah, and sir, okay. Now, how do I train such a network, even if I wanted to do a DNN, and then we will see how there is a better method called CTC to handle it. So, let me go back. In DNN what used to happen is I get the waveform. From the waveform, every 25 millisecond I extract the observation vector, the MEL filter bank vector, right. From the MEL filter bank, okay, now I have to, if I want to train the network, how am I going to? So, before I train the network, let me again make some of the terms and similarity to this thing very clear in your mind. These are the sound classes, okay. So, they are your equivalent of weather conditions, okay, which is always hidden from you. This is what you want to determine. Is the sound here, is the sound is the sound s, and so on, okay. And the language tells you how often given here the sound follows, and how often after the sound sir follows, and so on, okay. So, this we call as a transition probability. So, these are the nodes and these are the transition probabilities, okay. Then we are talking about hidden, the H part means hidden Markov model. In a hidden Markov model, I cannot directly observe the, in the case of weather, sunny, rainy or cloudy, because the saint is somewhere inside, deep inside the cave. Similarly, in the speech case, I do not know what the person had in mind and what is he vocalizing, okay. But I can observe the related phenomenon, okay, which is actually speech is measured, right. The rarefactions and compressions can be measured, picked up by the microphone. You get the waveform from which every 25 milliseconds I can extract the, physically I can extract these measurements, right. So, these are called the observation vectors, the MEL filter bank vectors. This is analogous to, I can, the saint sitting deep inside the cave and he cannot see the outside world, can still see physically what is the condition of the grass? Is it dry? Is it dryish? Is it damp? Is it so on? Okay, completely soggy or wet or whatever it is, right? Similarly, I as a human being can only observe this, and I am going to now make a decision whether if this particular guy belong to the sound. Silence is also sound. Okay, so that's an important category of phoneme, right? So there are these 45 e, u, but I also have silence to say that it's none of these guys, right? So therefore, does it belong to the class of sound phoneme, silence phoneme? This is also, is it silence phoneme, right? That is the whole idea that we are doing, right? So this now becomes a, if I am trying to predict, that means I have already got all these numbers, I already got the transition probabilities. On top of that, I need what's called the observation probability, right? The observation probability means I actually have trained the network and I found out how often given silence that I will be generating a vector like O3, right? So that is what we call as a likelihood, and so we have to have some historical data where I know the ground truth. From the ground truth, I am going to be able to learn the likelihood or the posterior in the case of DNN, and then for a new problem I can try to predict correctly what is the sequence of sounds. So to train the network, I need something called alignment. What do I mean by that? So again, I am going to repeat multiple times. I am going to draw this, but it will make your understanding a little more easier, right? So this is a waveform time, right? So this is a speech waveform S of t, and from which I am going to take some 25 millisecond thing, right? Now I am assuming over this 25 millisecond only one sound exists, right? And so this might be like when I am saying and, right? So another 25 milliseconds may start from here. Within, you might say, hey, this is confusing, but we do this for simplicity of math. There is an overlap. So if this belongs to one sound and let's say this belongs to another sound, in this region of overlap both sounds are there, right? So how do you say it belongs to one sound? Okay, so this is a deficiency of the method, but let us we have to make some assumptions, otherwise math will become very, very difficult and we cannot do anything in life, right? So these are, as engineers, we make approximation. Although I say this is one sound and this may be another sound and there is overlap, I say all of this belongs to only one sound, all of this belongs to one sound, and these two could be different sounds. Okay, I am going to assume, I know it is not perfect assumption, but it works in practice. Okay, so that is the way, what do engineers worry about, right? Researchers. And so one is math. Math says, oh, you cannot have all this ambiguity, right? But as engineers, we always make approximation. If it works, I am happy, right? So and it works, so we are happy. Okay, so we know that it's not perfect, we know it's actually not correct also, our assumption, but to make things work, I need to know this assumption of what's called independence is being made, and that's not correct mathematically, but it works well in the real world, these assumptions. I mean, even though we are approximating and we are making some not so correct assumptions, it does not hurt the final system. Okay, so from this I am going to take the vector O1, I am going to take the vector O2, right. So now in a DNN, what am I going to take? I am going to take the first part, right. So the first part that is there, and this first 25 millisecond, from that I am extracting this O1, the input node, this is input layer, okay, and therefore, and then this is the vector O1, then there are a lot of hidden nodes, and then I am going to have these, so these are hidden, this is the output, one of, let us say, 45 phoneme classes, and this is the hidden part. Now to train the DNN, I need supervision, right? I need supervision. I need to know what sound class it belongs to. So let's say we find out that this actually sound class A is what is there. So let's say this is the node A and this is the node IY, IH, some this corresponds to sound Z, this corresponds to sound S, this corresponds to whatever it is, you know, ch or something. Okay, so I am going to be having lots of things, and I know the truth is this is the supervision. I know for this particular part of the waveform, it belongs to sound s, okay, d. Okay, I think this is okay. So therefore, only this should light up, and all the others should go to 0. So this is the supervision that you are going to provide, or target. This is called the target. Okay. So what am I going to do? I am going to take the waveform, extract the MFCC vectors, pass it to the deep neural network. Now I am training the deep neural network. So I will first randomly initialize. Some values will come here, but my desired values only should light up. All the others should go to 0. So there will be basically only one of them that should be 0. So I use a softmax here. So again a softmax will come here. So softmax will come. Therefore, I can give an interpretation of probability, and only one of them should light up, all the others should go to 0, right. And therefore, but once I do random initialization, I will take a bunch of values and take an average error, then we back propagate, adjust the weights, right. Then another, it should be another batch, but let me take the second step of this. So let us say that I had done this, right. And then the next waveform I have found, which is 25 milliseconds. Again the same thing, for this part I take the MFCC vectors are coming here, Mel filter bank vectors or something. So this is my O2, right. Actually I will collect a lot of feature vectors and do averaging. A batch will be taken, but just to give you an example what happens to the second case, again there will be lot of these hidden layer nodes, right. Lot of these guys, right. And then at the output I will have these IY, IH, and somewhere AH has come, and let us say this guy is okay, and then some S's come, some Z's come, and so on. Now my target is what? I know that this is going to be, sorry, this is the target. This I know the sound is correct. Sound is, let us say, n, right. So only this. So the target, now I will tell this guy. So the target should be, all of these are 0, 0, 0, except for this guy who should be 1, and all the others should be 0. Like I am going to give a probabilistic framework that n should be the one that is correctly identified, all the others should go to 0. Again there will be a softmax here, right. So softmax will come, right. So that is what we are going to do, right. And then again there will be some error, I will back propagate and keep doing it, okay. So this is the way we are going to be proceeding, okay. So and then so if you look at it, and I will stop here. So if you look at the waveform, so this waveform, let me start here. So this waveform will be like this, okay. Then I am taking 25 millisecond window, okay. So this is another 25 millisecond window, this is another 25 millisecond window, okay. For this I extract the vector O1, for this I extract the vector O2, for this I extract the vector O3, sorry, and I continue. Now, each one of this, let me take this guy. This guy will become now the feature vector, then there is a hidden node, then the output node, and target, which will be some kind of a 0 0 1 0 0 0 0, something like this. This is the target. Okay. Similarly, I will take the other one. Again, it will be this thing. Again, the same hidden nodes are coming. Then again, I will get the output nodes, but now the target will be, for target here was here what we are going to do, we want n or something, target is equal to n. So, another, so one will be in a different position. Okay. So, and then similarly the third vector will come here, right. So, third vector is here. So, third vector is coming here. Again, I am going to take the input nodes, then the hidden nodes, then the output nodes, and again the target will be, let us say, target is d. So, this will be 0 0 0 0 1. Okay. So, 1 again will be in a different position. So, normally the way, and I will stop here, the way we draw this is that we will get a waveform. We will get a waveform, we will do window based analysis. Okay. We will get O1, which is itself a vector, which will be the input nodes first time. Second, you know, we will get O2, third we will get O3. All of these will feed into the regular neural net with multiple hidden layer. So, now I am drawing in the ulta, I mean now I have changed 90 degrees the orientation. So, this is the input layer, this is hidden layers, and then the output layers are here, the output layers are some guy, and for each of them this is the target T1, target vector T1, which will be 0 0 1 in only one position, target vector T2, target vector T3 will come. So, that is how we are going to give, right. So, if you look back at my slides, it will be clear, each one of them is generating a target vector. Okay. So, therefore, O1, O2, O3 need a corresponding target vector. Okay. This is called supervision. So, it is supervised learning. This is analogous to for every input, right. I have to diagnose, I mean the doctor has told me for these features this person is diabetic, for these features this person is not diabetic, right. So, now for every feature O1 I am asking what sound does it belong to, is it A or E or N or P or K, O2 does it belong to what sound, O3 what does it belong to what sound, right. So, those are the target, this is identifying one particular sound. So, one phoneme it is identifying, and what phoneme will depend on where you are putting the one, right. And therefore, for the supervision we need aligned information. So, we need alignment. for every MFCC vector, I need to know sound class during . Okay. And this is not an easy problem. I will talk about it next class. Okay. And so we can go to another method called CTC. Okay. So we will discuss this next class. Okay. Thank you.